In this video, we're going to look at ionic versus covalent compounds. First, I want to look at the goal of bonding. On their own, atoms are not necessarily in their lowest energy state. Atoms will bond in an effort to get to 8 valence electrons, be more stable and therefore lower in energy. They can do this by transferring electrons in ionic bonding or by overlapping orbitals and sharing electrons, like in covalent bonding. If you look on the left, it's an example of sodium chloride, where sodium has donated an electron to chlorine. That leaves behind a sodium ion and a chloride ion. The positive sodium ion is attracted to the negative chloride ion, and an ionic bond forms. We can contrast that with a covalent bond, where 2 hydrogens, each with 1 electron, overlap their valence orbitals, and now each hydrogen is associated with 2 electrons. But because it's the same 2 electrons for this hydrogen as it is for this hydrogen, they're really sharing those electrons. We're not going to talk a lot about covalent bonding now, other than just to contrast it with ionic bonding. The other difference between these kinds of bonding is with ionic bonding, we don't form a distinct unit of NaCl, but rather a repeating lattice structure in the ratio of 1 Na to 1 Cl. That is, lots and lots of Nas and an equal number of Cls all combined together. Likewise, with calcium fluoride, we have the same crystal lattice structure in a ratio of 1 calcium to 2 fluoride ions. Contrast that with covalent compounds, which are discrete or distinct structures or distinct compounds rather than repeating units. So we can draw the formula of a covalent compound rather than just give the ratio as in an ionic compound. Let's move on to naming these things. If you turn to the worksheet called Naming Molecular Compounds, we can get some rules to follow for correctly naming ionic and covalent compounds. The first thing we want to ask ourselves is to determine whether it's an ionic or a covalent compound, that is to say, an ionic compound or a molecule. You can ask, is it a nonmetal binding with a nonmetal? Another way to phrase that, is it 2 nonmetals? If the answer is yes, that's going to form a covalent compound. Another way to put that is 2 nonmetals will always form covalent compounds. If it's a metal with a nonmetal, that's going to form an ionic compound. The reason has to do with electronegativity, which we're not going to talk about now. We've already been over naming covalent compounds. There's just a few differences for naming, we've already been over naming ionic compounds. There's just a few differences for naming covalent compounds. First, you want to list the name of the first element in the formula. Then you want to list the name of the second element in the formula and add the "-ide" suffix. And we use Greek prefixes to indicate the number of each atom in the formula. So here's a test of how well you know your Greek. Can you try to match the Greek prefix with the number given? I'll pause the video and give you a chance to try it. Is this what you came up with? Let's do some practice. I'll leave the rules up above, do the first couple, and then leave the rest for you. Naming a covalent compound, we first want to identify what kind of compound this is. Bromine is a nonmetal. Iodine is also a nonmetal. 2 nonmetals means we have a covalent compound. Here I would write dibromine for 2, and then for 4, tetraiodide. What I've done here is replaced the ending of iodine with IDE, and because it's tetra followed by another vowel, an I dropped the A in the tetra and leave it as just tetraiodide. Next I have phosphorus and fluorine, both nonmetals, another covalent compound. The prefix for 5 is penta, pentaphosphorus. The prefix for 8 is octo, octafluoride. The last one, a single nitrogen followed by 5 oxygens. If there's a single atom in the first of the 2 elements, I don't put a prefix in, I don't put the mono prefix in. So this would just be nitrogen pentoxide. And again, I drop the A in the penta because the next letter is a vowel. Take a minute and try the next couple on your own. Once you've successfully written the names of those compounds, try doing the reverse and writing the formulas if given the names. Silicon dioxide, diarsenic, pentachloride, or sulfur pentoxide, and so on. We can make things a little bit more challenging in the next section by doing a mixed review of trying to name both ionic and covalent compounds. Let's start with a few examples of writing names and then writing formulas. Just as before, I want to look and see if I have two nonmetals, which would be a covalent compound, or a metal and a nonmetal, which would be an ionic compound. Potassium and phosphorus are both nonmetals, so I'm dealing with a covalent compound. A couple of atoms that are overlapping their valence orbitals, forming a covalent compound by sharing electrons. Following my covalent compound rules, this would be triphosphorus, tetrafluoride. Compound number 2 is the combination of potassium and oxygen. Potassium is a metal and oxygen a nonmetal, suggesting to me that this will be an ionic compound where potassium has completely donated its electrons to oxygen rather than sharing them. Following my rules for naming ionic compounds, I simply write potassium oxide. Notice that with molecular compounds or covalent compounds, I give the number of each atom. With ionic compounds, because the charge is known, it's up to you as the reader to establish the formula based on the name. Coming down below, trying to write formulas given a name, I see sodium acetate. Acetate is a polyatomic ion. Sodium is a metal, so we have an example of a metal binding with a nonmetal. And I can write the formula there. Nitrogen dioxide. I see the di prefix, which is a clue that I'm dealing with a covalent compound. So that'll tell me a single nitrogen and 2 oxygen. Try your best on the next several examples here, and then when you're finished there, move on to complete the chart, which is the same idea as above, just presented in a slightly different format.